A heat wave is hitting England and Wales this week, which comes with the usual reminders that all is not as it should be with respect to this planet's climate. It's 30 years since the Rio Climate Summit, where world leaders met and agreed that the environment was important enough to try and protect. And part of that protection involved building predictions of where we're heading, using climate models. But according to a paper out today in Nature Climate Change, the climate models we have aren't really up to scratch, and an upgrade would require more collaboration and some serious computing power. 9 of the world's leading climate scientists are behind the call, and joining me to discuss this is one of them, Professor Dame Julia Slingo from the Cabot Institute at Bristol University. Welcome to the programme, Julia, and what's wrong? Haven't we already got climate models?
We do indeed have climate models, and we've had climate models for nearly 50 years, in fact. But the problem is really that the granularity of these models is still very coarse. And what does that mean? Well, it means some very fundamental physics that we know is vitally important for predicting the course of climate change are not represented adequately. We've known this actually for decades, but it's only now that we have the computing power to really address this shortcoming in the models. And it's important to emphasize, I think, that things like temperature, which we always associate with global warming, of course, and with climate change, is relatively well handled by these models and has improved dramatically since Rio. So we do have a sense of the level of warming risk that we face. But when you come to something that's equally fundamental to our lives and indeed to all life on Earth, fresh water, therefore rainfall, we have very little confidence in what these models can tell us. And that's because the physics works at the scale of the clouds, and the clouds are very fine scale. So we are really now, I think, questioning where we're going with our mitigation and adaptation efforts. We need to know what the future of our fresh water is. If we're to build nature-based solutions, as we say we want to do, then this fundamental shortcomings in our current models will mean that all the information on which we build those measures is frankly inadequate. We only have to look at last year's extreme events that were frankly almost unimaginable. The flooding that was seen in Germany and in Italy and around the world was just way outside what these current models can tell us. And yet we know that if we can represent the physics more completely, more accurately, we can do a much better job.
Well, I was reading about the floods in Yellowstone Park this week, and
Yes.
One of the park rangers was saying this kind of event is not unexpected, but we didn't actually have the capability to predict this particular thing. And that seems to be what happens a lot with extreme events. You know, they'd be classed as weather before rather than climate events. And although they're increasingly linked to anthropogenic climate change,
Yes,
they're not really predictable. Are you saying that we want the kind of modelling capability that would allow you to predict them?
it's not that they're not predictable in a sort of weather forecasting sense. The fact is that our current climate models wouldn't even contain events like those because the physics is not in those models to produce them. And that's a really fundamental point here, that we don't know what we're going into in terms of the intensity and frequency of extremes. And I have to say that this fundamental physics that I'm talking about is also actually goes much bigger than that, because we actually really don't know how big things like the big waves in the jet stream that we seem to see more frequently, those are all driven by rain-bearing systems in the deep tropics. And if we don't represent those, then we do not know what will happen to, say, our jet stream and our weather regimes in the future. nor do we know actually what our cloud feedbacks will be, and therefore how sensitive our climate is to increased greenhouse gases. These are some very fundamental questions that are still out there and cannot be answered unless we start resolving the water cycle, the clouds, the water vapour, the rainfall, as accurately as we possibly can, capturing those fundamental physical processes that are essential, and they happen at the cloud scale.
So to get the models zoomed in from the current 100 kilometre scale down to the 1 kilometre cloud scale, it sounds like that would take a lot of computing power, and that sounds expensive.
And it is, and I think this is why we've been so slow to pick up on this. The history of every country having its own climate model and producing projections to go into the IPC has been a great thing, but actually it's held back, I think, the progress of climate science. Because to do this cutting edge modelling, and we can do it, we've demonstrated that in the last few years, we do need very, very large supercomputers to do it. And I think it's time to move now from a paradigm which is all about individual nations to one where we have an international consortium, well-resourced and with the technology that's needed, so a dedicated exascale computing system where we can do these as a joint endeavour internationally. It's not unlike, actually, the particle physicists all those years ago deciding that they needed a Large Hadron Collider to find the Higgs boson. We believe we need the equivalent of that now to be able to say what our future climate is going to really be like in terms not just of temperature, but of the availability of fresh water, of extreme events, of all aspects of the science of climate change. It's time to do this now. We have the pieces in place. It just needs the international will and investment to do it.
And how much investment?
Well, it's actually, in the grand scheme of things, fairly modest. We estimated about £250 million a year.
Julia, that sounds like a huge amount of money to me.
Well, it doesn't if you think that the Large Hadron Collider has cost $10 billion.
True.
Yes, and so I think that if we're talking about what is the future of a sustainable planet and how do we make decisions with more certainty, especially involving water, which is, after all, Earth's lifeblood, I think £250 million a year is a small change, actually.
Well, you've said it. The science is out there, and I look forward to it being on the agenda at COP27.
So do I. Thank you very much.
Thanks, Julia Slingo, Professor of Climate Science at the Cabot Institute.